Good morning, and thank you for joining today's webinar from Spec Innovations, a digital engineering case study for aerospace. My name is Taylor Duffy, and I will be the moderator for today's webinar. First, I would like to go over some housekeeping. Next slide, please. During the presentation, feel free to send us questions and we will get them answered in the Q&A part of the webinar. You can also interact with us on LinkedIn through the Innoslate users group or through X using the handle @SpecInnovations. The webinar is being recorded and will be made available to you after the live presentation, so keep an eye out for it in your inbox. Next slide. Now I would like to introduce you to our guest speaker, Sabrina Barm. Ms. Barm is a research associate and PhD student at the Technical University of Applied Sciences, Oxford. With a background in mechanical engineering and structure concept design and several years of automotive and aerospace industry experience, Sabrina Barm joined the research group THA Composites at the Technical University of Applied Sciences of Augsburg, Germany, as a research fellow and PhD student in 2021. Her research is in the field of hydrogen air mobility and model-based systems engineering. Her focus is on predictive system modeling, which supports physical system design at all system levels, and on integrating causality to explore causal relationships between system characteristics and behavior. Feel free to email her any questions at sabrina.barm@hs-augsburg.de. And now I'll hand over the controls to Sabrina and we'll get started.
Thank you so much, Taylor, for this kind introduction. Thank you for having me. I'm really excited I get to share some of my work with you today. At first, I'll introduce our general system design and system modeling approach before going into greater detail on our behavioral model and the test prediction we did on a component level to verify the system function, as I said, on a component level. And I'll also talk about a comparative test post-prediction we did to see how accurate our models are. And at last, I'll explain what a fuzzy causal network is and how we're using it in our modeling approach. And then I'll conclude with a conclusion and hopefully equally exciting outlook. Now, the systemic context we're looking at is a hydrogen fuel cell powertrain for a regional distant aircraft. The hydrogen as energy carrier for the powertrain is stored in liquid form, in cryogenic form, which is really cold. It has a temperature of about 20 Kelvin or minus 250 degrees Celsius. I'm sorry, I don't know what that would be in Fahrenheit. And as its motor, it uses an axial flux motor, which is a special type of electric motor. And what's even more special about that motor is that its cooling system uses the cryogenic hydrogen as its cooling medium. Now it's easy to see how such a system is extremely complex. We're having extreme temperature differences, extreme requirements. And our mission is really simple. We do want to design an optimal system, but in light of all these complex and extremely challenging, demanding requirements, how do we do that? How do we slay such a dragon? And in order to build or even just design a system, we need to understand it. And to understand a system, we can model it. And that's what would help us to really go into our details for the system. And our modeling approach is a three-way approach. We're using a descriptive MBSE model to capture and develop all our system relevant information, to synchronize it and to visualize it. We're using a MBSE behavioral model to represent the system function and research its behavior. And as our third step, we're using a causal network model to research causal relationships, causal chains within our system. Since when developing a system model, we need to define not only what our system needs to do and what requirements we have for the system, we also need to define what our model needs to do, what questions our model needs to answer. And combining all that, we can gain the understanding of our system through our models and at last reach an optimal system design. So how do we start? What are we modeling? We're modeling a cooling system. We've established that. And to figure out what's happening, what is the background of our system, we're looking at an aircraft mission profile of our regional distance aircraft, which gives us our operational need, telling us to fly that mission profile, we need a certain motor performance, which delivers our meta requirement. And knowing that performance need and the motor efficiency, we can derive the loss performance. How much heat that is generated needs to be transported out of our system, and that delivers our system functional requirement. And now we need to identify what that requirement needs, which physical processes govern and describe our system behavior. And to describe them, to represent them in our model, we need to identify appropriate and meaningful abstractions. I mean, we've all heard before that all models are wrong and some models are useful, and it's these meaningful, useful abstractions that make our models useful. In the case of our cooling function of our system, we're talking about heat absorption of the waste heat that is generated and its transport out of the system, which means we need to identify what happens in terms of heat input and how to get it out of the system when we're using a cooling medium, which means to describe the flow behavior of our system. Generally speaking, our model looks like this. We've opted for the concept of a hollow conductor cooling system, which means that inside the electrical windings of the electric motor, where the greater part of the waste heat is generated, there's a cooling channel inside these electric windings. And the cooling behavior is described through the flow behavior, which is, again, characterized through the temperature change, indicating a heat absorption. And it's also characterized through a total exit pressure and a pressure drop, indicating the quality of the mechanical flow functionality. And why is that important? Looking at the greater systemic context of the powertrain, we have the requirement that we need to operate the cooling system without an explicit pump. So we are required to have a certain exit pressure at the exit of the cooling system. And the control and input parameters of this cooling system are the mass flow of the cooling medium, the hydrogen, the entry pressure, and the entry temperature. Our behavioral model we're looking at now is the model of a singular component, the main component of the cooling system, which is the coil, the hollow conductor coil. And our objective for that model, what questions does this model have to answer, is to see what are the functional ranges of our system and where does the system not work? What are the limits for the entry parameters I run the system with? So in other words, we use this model to run test prediction and create data to evaluate a design of experiment for the component tests we also did on that level. And that model served its purpose well. We could establish where the functional ranges are. For example, the entry pressure needs to be above 5 bar, and when we lower the entry pressure below 2 bar, we have a flow stall, which means the cooling medium flow is not happening anymore and the cooling system's not working outside of that range. On the model architecture side, we're looking at it's a classic action diagram in Innoslate, LML diagram, and we're looking at 2 update blocks and calculation sections. Inside these action blocks, we're running JavaScript code. At first, we have the update 1, which picks up static system characteristics, which are stored in the form of characteristic entities in a spider diagram, which serve as our repository in that case. And the update block 2 does something very similar, but for resource variables. That would be temperature, pressure, any variable that really changes throughout the cooling process. And we've represented those through resource entities, and the repository is, in this case, a very simple decomposition diagram that we can enter and change the entry parameters and run scenarios with the system. And in the calculation blocks, we can represent the physical system behavior through scripted equations in the JavaScript syntax. And at last, we get an output in terms of exit pressure and exit temperature. And yeah, I'd like to give a short demonstration. I'll be trying to go into the live model. Now, these are the system characteristics. They don't really change, they're statics. And now let's see what entry parameters we have. Yeah, we have an initial entry temperature of 120 Kelvin, an initial pressure of 6 bar. And let's see what the cooling system does. What I've been doing here is I'm tracking the final amounts of, let's let it run since it'll be running for a couple of seconds. So what I'm doing here is I'm tracking the final amounts of our exit pressure and our exit temperature. And I'm also running a console to see if anything goes wrong during the simulation. This is quite helpful. And now the simulation is complete. We're looking at an exit pressure of 4.8 bar, which means we have lost about 1.2 bar, which was to be accepted for that system, and the temperature has risen by 60 Kelvin, which was also to be expected. And now let's see what happens if we change something. We're going back into our resources. Let's make this a little warmer, 150 Kelvin, and I should probably save that. Happens every time. And let's increase the pressure a bit. All right. And now we'll run the simulation again. Now it's going to take a short while, but this is still a fairly good approach to really test what the system could be doing before you're heading into really expensive tests. And here we have a lower pressure drop by only 0.9-ish bar, and we have a fairly similar temperature rise. So this is also in the expected values, and this was just a short demonstration to see how you can try out different scenarios for the system operation. Derived from those test predictions, we created a design of experiment that you can see in a simplified overview here. And what we decided to do in our tests is to run different series, varying mass flow and entry pressure, and also the amperage, the strength of the electrical current, which means varying the heat input. What is not varied here is the entry temperature. Now that is usually something you would also like to vary and see what happens, but we had a few limitations with our test equipments since this was not a standardized test. Nobody had ever really done something like that before, so there were no test standards to rely on, and we had to sort of wing it. And we realized that it was too difficult to maintain the temperature at a stable configuration after changing it, so we just stuck to one temperature. And the test setup as such in the experiment looked like this. We had a hydrogen tank and a heat exchanger to cool the hydrogen down to a cryogenic temperature. And the test specimen, the hollow coil conductor, you can see a little CID screenshot here, or the photograph of the actual specimen here, was inside a test chamber or box that was filled with gaseous nitrogen. Since at these temperatures we're dealing with, there can be quite some issues with icing, even if you apply electrically induced heating. You can see that on the next slide. We have applied a fairly strong electric current, about 300 ampere, and we still have quite a bit of icing, or in the top view. So that was a pretty exciting test. And the data we gained from that testing was used to run back in our model and see, is our model actually accurate? What we're looking at here is a test series where the entry pressure was kept static at 6 bar, and we varied mass flows and electrically induced heat input. And the dots are a little small. The lighter colors are the MBSE values, the darker colors are the experimental values. And what you can see looking at those results is that in its superordinate behavior, in its patterns, the MBSE outputs correspond to the behavior we've seen in the experiment, although the temperature outputs exceed the experimental values by 5 to 10%, especially at higher amperages, at higher electrically induced heat input, which for a system level model, this is not a detailed FEM or CFD simulation, is in an acceptable range. But when we did more tests looking at the pressure behavior, we see that, again, the superordinate behavior patterns align with each other, but in the pressure outputs, the MBSE values exceed the experimental values by 7 to 12%, which is not quite as nice anymore, and we do have significant outliers. And overall, that means the model generally works, but the accuracy needs to be improved. And what we've also seen looking at data of our tests and our models is that a lot of parameters not only influence the overall system behavior, but also seem to influence each other. But it's impossible to tell just from looking at graphs and diagrams of our data to tell which causal chains meaning the path from a cause to its effect, are really happening, and which influential relationships we have, and also how strong they are. But that is something we would like to know. When I change the entry mass flow, it will also influence the entry pressure and the pressure change. But how strong is this influence? And if I want to control and operate my system, it would be great to know just how sensitive that system is in its behavior to changes in either input parameter. So what a fuzzy causal network here is supposed to do, we're using the method of fuzzy cognitive maps here, is to do just that. It's basically a sensitivity analysis, but representing and respecting complex feedback loops. And we're also implementing learning algorithms to run a pattern recognition to research the trajectory of our influential relationships. Now, fuzzy cognitive maps are a specific type of neural network, and they capture system-relevant parameters with their states and their relationships between them. And the beauty of FCMs is that they're integrating fuzzy logic, and fuzzy logic can be explained as mathematically normalizing any kind of value or range onto a fuzzy interval from either 0 to 1 or -1 to 1. And by that fuzzification, that mathematical normalization, we are able to compare the incomparable, meaning comparing values of various domains or largely varying magnitudes. And now we tried to model our system behavior in such an initial fuzzy cognitive map. The little blue dots here are representing our influential parameters, which are our input parameters, and the output parameters we're monitoring, and the relationships between them. And as I've tried to explain before, the objective is to identify the nature and the strength of relationships within the system and the system behavior, to learn if I change a parameter, how strong is that effect. And using our experimental data, we've run we've used a Hebbian learning algorithm to run a pattern recognition, and looking at that result, it looks pretty similar to what we've just seen. We see that the trajectory of our influential relationships has not changed, and the values have changed a little, but they have all changed in the same way. And that could tell us that qualitatively our initial assumptions about the causal relationships in that system might be correct. However, we need to consider that we had been using a really small data set of only 23 data points, and that is really small for a pattern recognition. And while working with that method, we have also realized that the results of such FCM are really sensitive to model settings and changes in the model settings, and also tool issues. So it's somewhat, I wouldn't say novel method, but it's not as widely used, and we saw that it's due to quite a few challenges, but that will not stop us. So how are we using that fuzzy causal network in our overall approach? I've explained before that we've used a descriptive model to capture and develop our information that is relevant to the system. We're using the behavioral model to simulate and predict the system behavior, and we're using the causal network model to learn about the relationships and its sensitivities, and at last to be able to control them. And that will lead us to an optimized system design in its architecture, in its behavior, and in its controllability. Summing this all up, we've seen that, or we found in our work that the general MBSE capabilities are invaluable to our development process. And even though our behavioral model was limited in its accuracy, it was already a really valuable tool for the test prediction and the DOE creation, allowing us to find the functional and non-functional ranges of our system. And while the FCM also require a lot of refining, they've shown us that understanding causality means understanding the system and helps us to make well-targeted design decisions. All of that, of course, is not the end of the road. This is where the fun begins. We're now working really hard on improving the accuracy of our MBSE behavioral model, and we're working on gaining a larger database through simulation and further testing to remodel our fuzzy causal network and gain a larger causal knowledge base. And we will integrate all that to do a test prediction and DOE for the physical testing of a demonstrator of our global cooling system and motor. At this point, I have to express my thanks to everyone in my team. They're really awesome. I'd also like to thank Stephen Dam and Taylor Duffy from Spec Innovations for having me and giving me the opportunity to present today. And thank you all for listening. And that would lead us to our Q&A.
Great. Thank you, Sabrina. If you haven't done so, please send your questions through the panel on the right that pops up after clicking Q&A on the top bar. Next slide, please. I hope everyone enjoyed this special webinar. If you're interested in having our team help you start applying Innoslate to your project or system, contact our sales team. You can reach our team by email at sales@innoslate.com or through our website, specinnovations.com/contact-us. So we received several questions already. We will answer as many questions as we can before our time is up. First question is, how does the MBSE approach enable scenario analysis and comparison of different system configurations?
Thank you for that very interesting questions. In the characteristic, in the characteristics and in the repository, we have stored system configuration parameters that we can alter. We can, for example, alter the length or the dimensions of our hollow cooling conductor. And that would allow us to see what if we were using a different electrical winding, how would that affect the cooling and overall system behavior.
Next question, what are the limitations of MBSE in analyzing system behavior?
I'm sorry, could you repeat that, please?
Yes, what are the limitations of MBSE in analyzing system behavior?
The limitations are in the level of detail and in the abstraction. At some point, that's actually one of the advantages of using a system model in the form of an MBSE model, since you abstract the system behavior and can therefore more easily represent larger and more complex system. But in order to be able to do that, you need to simplify a lot of things, and the art is to make the abstractions just right so no valuable information gets lost.
Great. Next question. What modifications are planned for the MBSE model to improve its predictive accuracy in future iterations?
The main changes we're doing is changing the way we've modeled the heat input. Since when we did those initial models, we thought that any external heat input would be neglectable. And after comparing the test results with our MBSE simulations, we've seen that there was quite a few differences, especially in the pressure behavior, which is strongly influenced by the temperature change. And we realized that external heat input from ambient air, for example, is actually quite significant.
Great, thanks. That looks like all the questions we have for now, but you guys can reach out to us through our website, email to ask any more, or directly to Sabrina. If you'll go to the next slide, please, I'll close this out. We would like to thank you again for joining us today, and a special thank you to our guest speaker, Sabrina. As a reminder, we will be following up with you very soon to send you a link to the recording and the presentation slide deck. We hope you can join us for next month's webinar, Streamlining Requirements Management with Innoslate, a complete guide, with Dr. Stephen Dam on Tuesday, April 22nd. Your link to sign up will be in the email that is coming soon to your mailbox with the slides and recording. Next slide. We also encourage you to visit our website and our blog, as well as connect with us on social media. That concludes today's presentation. Have a wonderful day, and we hope to see you at our next webinar.